In the second part of this lecture, we will be discussing Gauss theorem or Gauss law, which is one of the most important laws in electromagnetics. And I did mention it before because it is one of the four Maxwell's equations. We talked about there are four Maxwell's equations in integral form and differential form. So Gauss law is one of, it has both an integral and differential form as one of them. And it was formulated by the German scientist Gauss in 1835. So he was able to relate the electric flux flowing out of a closed surface to the charge enclosed in the volume surrounded by that surface. So what is the statement of this law? Simply says the electric flux through a closed surface is equal to the electric charge enclosed by that surface. So if there is no charge inside the surface, this means there is no net flux. Net flux must be zero. There will be only a net flux coming out from the surface if there is a charge inside. And if it's a positive, net positive charge, then the net flux will be positive. If it's a net negative charge, then the net flux will be negative. And so mathematically is how we write it. Say the total flux epsilon is equal to the integral over the closed surface of d dot ds will be equal to the charge enclosed q within this surface, but the charge q enclosed within the surface equal to the integral over the volume enclosed by this surface of rho v dv, where rho v is a volumetric charge density. Because if you integrate the volumetric charge density over any volume, this will give you the total charge inside that volume. So now what we have that epsilon is equal to integral, closed surface integral of d dot ds. It equal to the charge enclosed equal to the total volume integral of the volumetric charge density. So if we want to know the charge inside a surface, what we have to do, we have to carry out a surface integral of d over this closed surface to get the total charge inside. Now, if you apply divergence theorem tells us the integral over a closed surface of d dot ds is equal to the integral over the volume surrounded by that surface of the divergence of d volume. Remember, divergence of a vector is a scalar. So it's now a scalar. So this is now divergence theorem, and this is because of Gauss law. This must be equal to this term as well. So now we have two volume integrals. One of them is the integral of divergence dd volume. The other one is the integral of rho volumetric d volume. So this is simply saying that if we integrate over the same volume, divergence d, the integral of divergence d is equal to the integral of rho v. Now this can only happen for any arbitrary volume if at every point in space divergence of d is equal to rho v. And this is called Gauss law in differential form. And I mentioned this before when I told you that the divergence is a measure of the sources. If you want to measure there is a source or not at a point, you find the divergence at this point. So divergence has its own mathematical expressions, but its meaning is simply the source, the density of the source at that point. So now we have a number of very interesting tools that we can use. If we want to get the charge within a surface, well, we integrate over this closed surface. Of course, talk about the closed surface, d of d. Get the total flux, electric flux through that surface. This will give us the charge. And if you want to calculate the volumetric charge density at any point in space, if d is given, then find its divergence. And the divergence will tell you at every point if we have a volumetric charge density. And as I mentioned earlier, this integral form here and this differential form here, they are both part of Maxwell equations. The 8 Maxwell equations, the 4 differential equations, and the 4 integral equations. And these are the laws governing electromagnetics. We have here an illustration of Gauss law. So you have here a surface V1. It's a closed surface. And it's enclosing two charges, a point charge minus 5 nanocoulomb and a volume charge of 10 nanocoulomb. Maybe it's a certain subset of this whole volume. Then what is the total charge surrounded by this surrounded by this surface is equal to 10 nanocoulomb minus 5 nanocoulomb, so it's equal to 5 nanocoulomb. So if you carry out an integral of d dot ds over this surface, the answer must give you 5 nanocoulomb. regardless of anything else, regardless of how the charges are distributed. As long as we have 5 nanocoulomb inside the surface, the answer or the total flux out of that surface will be 5 nanocoulomb. Now, take another situation where you have a closed surface here, but inside it there is no charge. There's no charge enclosed. Then, even though there are charges just outside the surface, the net flux over this surface must be zero. The flux flowing in will be equal to the flux flowing out. There is no net electric flux. So it all depends on whether there is a charge inside the surface, inside this closed surface or not. Even though Gauss law applies to any type of closed surface, any closed surface, and any distribution of charge, Gauss law still applies. But its great application is for problems with symmetry. We have seen before in the previous lecture how many of the problems we try to solve end up with extremely tough integrals to calculate. But if you have problems with symmetry, Gauss law gives you the answer in a very easy way. And these are the procedure that you have to use in order to properly use Gauss law. You have to select what we call a Gaussian surface. Remember that Gauss talks about a closed surface. So you have to select a good Gaussian surface, a good surface where we can apply Gauss law. And this surface should be selected such that the vector D is either normal or tangential to the surface at every point. Why is that? Because if it's normal, then there is no flux at this point. D dot ds will give you zero. If it's normal on to the surface, d dot ds, d and ds will be in the same direction because ds as well is normal to the surface, and their dot product will end up with a scalar product. So they are in the same direction. So the cosine of alpha between them will give you 1. Then you end up with this scalar. And if D is tangential to the surface, then D is normal to the surface area or the differential surface vector, and this will cancel out. Now, when we select for parts where D is normal to the surface, D must be constant. So we have to select it that way. And this comes from the symmetry of the problem. Now, if this is the case, if it's constant, then d dot ds, because they are in the same direction, will give you d ds. But because d is constant, I can take d out from the integral, and then I integrate ds, and this will give me the total area of the surface. And then I can obtain my solution by dividing the total flux, which I calculated, over the total area. So now this is a procedure. Gauss law applies for any distribution. It doesn't matter. Any surface, any discharge distribution. But it's a great application for problems with symmetry. And to be able to obtain it to solve a problem, you have to select a good Gaussian surface. Good Gaussian surface is one where D is either normal or tangential to the surface at every point. If it is normal, this is fine. D and ds will be in the same direction. This dot product becomes a scalar product. If it's a point at where it's tangential, d dot ds will give you 0. And we end up with zero contribution. For this part, when it is normal, D must also be constant over the surface. So in this case, when I carry D dot ds, because they are in the same direction, cosine alpha between them is 1. This will give me d ds. But if D is constant over the surface of integration, I can take it out from the integral, and then I can simply integrate ds, and the integral of ds will give you the total area. Now let's take a look at a number of classical examples where Gauss law can give us the answer in a very easy way. So here the first one is a very simple case where we are talking about a charge at the origin of value q. We'd like to determine the vector d and e everywhere in space. Well, from the symmetry of the problem, I can tell that the electric field must be in the radial direction, so it must be in the AR direction. So here it is this direction, here it's going to be in this direction, here in this way it's going to be in this direction, so it's always pointing in the radial direction. And because of the symmetry of the problem as well, I can say that the electric field, if it's getting weaker, it must get weaker as we move away from the charge. So it is a function of R. So now if I select my Gaussian surface as a sphere with center at the origin, this will satisfy the conditions I'm saying, because D is normal to the surface at every point. D is always in the AR direction. And when I select a sphere with a constant R, and because D must only depend on R, D will be a constant. So now we can apply the Gauss law. Gauss law is saying the surface integral, closed surface integral over this surface gives me the charge enclosed, which is Q, because I have a point charge at the origin. So now, because D is normal to the surface, D is in the same direction as ds. So here, for example, I can select a Gaussian surface element, rho squared sine theta d theta d phi. This is what this surface element, and then I do my integral, okay? But because D is normal to the surface at this point, this product here will give me dr, the component of D, which I do not know because D is fully in the R direction, in the radial direction, multiplied by ds. But because my surface is a sphere and D decays only with R, and the R over every point here is a constant, then I can simply take dr out from this integral. And I end up with the integral of ds. Integral of ds over a sphere will give you the area of the sphere, which is 4 pi r squared. So now, this is the expression that we have. The total charge enclosed, which is Q, is equal to 4 pi r squared multiplied by dr. So now I know that the dr, the D component is equal to Q over 4 pi r squared. And if I want to get E from D, I simply divide by epsilon. Remember, D is equal to epsilon E. Then E is equal to D over epsilon. Now, this expression here is the component itself. If you want to get the electric field, of course, the electric field is equal to this component in the R direction. If you want to write it as a vector. Okay, this is exactly what we got before using Coulomb's law. And the good thing about this is that the way we selected the Gaussian surface, we selected as a surface where D is normal to the surface at every point, and where D is a constant because of symmetry, because D depends only on R. So if I fix R, if I select a certain sphere, D is fixed over that surface. A second example that we can also find useful, and we have seen this before, this is not a new example, we have seen it before, but we derive the expression using a completely different technique, is a case where you have an infinite linear charge, so an infinite charge extending from minus infinity to infinity. And because of symmetry of the problem, I can immediately tell, and as I explained earlier, the field must be in the radial direction, because every component, every element here will cancel with another element. They cancel the z component, and only the rho component will remain. And because of the symmetry of the problem as well, I can simply say, if I take a top view, if I simply look here from the top, okay, I will see my point, my line charge as a point, and the field is pointing in the radial direction, in the rho direction. And because of the symmetry, the field will decay only with rho. So the field is only a function of rho. So now if I select a constant rho surface, then D will be constant over that surface, and I can apply Gauss law. And this is what I did here. I selected my Gaussian surface as the surface of this closed cylinder. This closed cylinder has three surfaces: the top disk, the bottom disk, and the side wall. And the flux through the top disk and the bottom disk is 0, because D is in the radial direction, is in the rho direction. So it's tangential to this one, it's tangential to this one. While D is normal to the side surface. And because D is normal to the side surface, what we can do, we can simply apply Gauss law. We can apply, say, the integral over this closed surface will be only the integral over the side surface of D dot ds. What is ds here in this case? As we studied earlier, if you draw a surface element here, tiny surface element, this one here is rho d phi, and this one here is dz. So it is rho d phi dz, and also in the rho direction. So we can see that d and ds are in the same direction. So the scalar product will give me a dot product. Okay, and because I selected my side surface as a cylinder centered at the around with this axis, with z axis, its axis here. What is happening is that d rho is a constant at every point on this surface. Because d it changes with rho, and rho is a constant. I'm picking only one Gaussian surface, so I can take d rho out from the integral. Okay, and then I'm now integrating the side area of this cylinder of length L. Of course, I'm picking a one with finite length. What is the side area? It's simply equal to the circumference 2 by rho multiplied by L, by the height of this cylinder. Now, what is this integral equal to? Is equal to the charge enclosed by this cylinder. The charge enclosed is equal to the linear charge density multiplied by the length L, because this is a charge inside the cylinder. So it's rho L multiplied by L. Remember, rho L is in coulomb per meter. It's a linear charge density. So if multiplied by the length L, it gives me coulomb. So here, if you equate these two, what you can do, divide this term here, by this term, and you end up with the expression for d in the rho direction. As we agreed, if you want to get E from D, divide D by epsilon. So this is exactly the same one that we got earlier by doing very complex integrals. And you get it here in a very easy way, or very simple way, due to the high degree of symmetry of the problem. Of course, I'm not showing the exact vector expression, but the vector expression, as we obtained it earlier, will be E rho in the rho direction. So it is rho L over 2 pi epsilon rho in the rho direction. So this is a second application for Gauss law. A third application for Gauss law that we also have seen earlier is how to calculate the field resulting from a surface charge. So we have an infinite plane with a surface charge density of rho s coulomb per meter squared, and the charge is over this plane. From the symmetry of the problem, we can again conclude two things. I will draw here for you the plane on the side. Because of the distribution, every element here and every element here will cancel each other out in the x direction, y direction, and the field will be only in the z direction. Okay, so from symmetry, we can simply say field is only in the z direction. And because of symmetry as well, I can say that the field will decay away from the plane. So it's only a function of how far are we from the plane. So it also decays or changes along the z direction, if it changes along the z direction. So by knowing that, we can select a Gaussian surface as shown here. Why this one is good? It's very simple, because we know that D pointing normal to the plane here and pointing downward on the other side. So the flux through all the four side surfaces will give you 0. It's only the top surface, this one here, and the bottom surface here that will give you a value for the flux. So we selected a surface where D is tangential to 4 of the sides, and it is normal to this one and this one. Now, one other thing, because the field, if it changes, it will change with Z, and this is a constant Z surface, this one is a constant Z surface, then D will not change at every point here on this surface, and I can take it out from the integral. So what we say here, we say that the total flux through this whole closed surface will give us only the flux through the top and the bottom plates, because D is in the Z direction, it is normal to all the side surfaces. Now, this one is in the Z direction, and the unit area as well in the Z direction. This one here is in the negative Z direction, and the unit area is also in the negative Z direction. So there are two negative signs, they cancel each other out, and the result is double what you get from the top integral. Now, because D and ds are in the same direction, the dot product became a scalar product. They are in the same direction. And because dz is constant over the surface here, over this top part, I can take it out from the integral. So this will give me 2dz multiplied by integral of ds. But if the area of this element is A, which is the same as this area here, this will give me 2za. And this 2za, according to Gauss law, is equal to what? Is equal to the charge inside this complete closed surface. What is the charge enclosed? It is equal to the area, this area here, multiplied by rho s. This is a charge inside. So the rho s multiplied by a, and rho s here is in coulomb per meter squared, is equal to 2za. Divide this side by this side, you get that dz in the top part is equal to rho s over a, or that ez is equal to rho s over 2 epsilon, because e is deducible from d by dividing by epsilon. And you could see here the selection of the Gaussian survey is what made the complete difference. So the electric field, of course, if you want to be accurate and write it in an accurate way, you say the electric field is equal to rho s over 2 by epsilon a normal, where a normal is z in the top part and a normal is minus z in the bottom part. Okay, this is a more accurate mathematical expression for that. The last case study, and this also is not a new result for us, we have seen this one before. What if you want to calculate the electric flux density resulting from a sphere like this one here? So this is a charged sphere. It has a volumetric charge density, uniform volumetric charge density, rho volume coulomb per meter cubed. How can we get the total field inside and outside? Before we're not able to get the field inside. It would have been extremely difficult. But now we can get inside and outside using Gauss law. Let's see the procedure for that. From symmetry, and I don't think I need to explain this too much, the electric field resulting from this structure must be in the rho direction. And because of the symmetry, again, the electric field will only depend on R. So these two things, these two givens, makes me immediately select my Gaussian surface as a sphere with a center at the origin. When you do that, the vector d, which you can draw here, the vector d will be normal to the surface at every point, because d is equal to dr in the r direction. It's normal to the surface. And if you select a constant r sphere, this will give you a constant value for dr over the surface. So what we do here, this is our sphere. The Gaussian surface is this one. This is R here, okay? So I will first select R to be smaller than A, and I apply Gauss law. What is the field, what is D at every point on this Gaussian surface? Before we're just getting D outside. Now we're getting D inside as well. We apply Gauss law. The integral of D dot ds is equal to the integral over this surface of dr multiplied by ds, because they are in the same direction, the radial direction. And because my surface is a sphere and dr is a constant on the sphere, I can take dr out from the integral and multiply by the area of this one. So the area here is 4 by r squared. But what is the charge enclosed? The charge enclosed is simply equal to the volume surrounded by this sphere of radius r multiplied by the volumetric charge density. This is what you have here. It's 4 over 3 by r cubed rho v. So now I can get dr by dividing this term over this term, and I get this interesting expression, which shows me that the field is increasing with r, is not decreasing with r inside the sphere. So from here to here, until you reach the edge of the sphere, until you reach the sphere itself, the field is increasing. Okay? What will happen if I select my Gaussian surface outside? Everything will be exactly the same. The integral of dr dot ds will give you dr 4 by r squared, but the only difference is that the volume the charge enclosed is the total charge inside, not only part of the charge as shown here. This is part of the total charge, while here this is the total charge. What is the total charge? It is the 4 over 3 by a cubed, not r cubed, a cubed multiplied by volumetric charge density, and this will give us a completely different expression. So you do exactly the same for the outside, and the only difference here is that before this was r cubed, because we're only picking part of the charge. This is the total charge inside the sphere. It is the volume of the sphere multiplied by rho v. This one is still 4 by r squared, because the Gaussian surface, it can be at any r. So if you divide this one by this one and you cancel common term, this is what you'll end up having. This is the total charge Q divided by 4 by r squared. Or you can, of course, if you cancel the by and so on, this is another expression. This is the same result we got earlier using a very complicated integral. That the d at any point, or the electric field actually is talked about, is equal to q over 4 pi epsilon r squared. So we said that this charge looks like a pointed charge at the origin if you try to see its field from the outside. And this is exactly the same result that we get using Coulomb's law. Now, if once I have d, of course I can get E, because ER is nothing but q over 4 pi epsilon r squared. It is dr divided by epsilon, and I know, of course, the direction of the electric field. Now let's see some examples on this one. We have a thin spherical shell of radius a, carries a uniform surface charge density rho s. So it's a shell like that of an eggshell, very thin. It's carrying a surface charge density. We would like to get the field everywhere, inside and outside this shell. This is not one of the classical examples. It is not a point charge. It's not an infinite line of charges. It is not an infinite plane. It's not a charged sphere. But it's another example where the high degree of symmetry makes applying Gauss law very attractive. Of course, as I explained earlier, we start by drawing a diagram. This is a sphere here, and you can see the charge is on the surface. It's a shell, starting on the surface, okay? Now, because of the symmetry, the D, or the electric field, will be in the radial direction, and it will change only with R. So if I select my Gaussian surface as a sphere at the origin, which is a constant R surface, then in that case, D is normal to the surface, and it's constant over the surface. Now, if I select one as a Gaussian surface inside, so here, this is the radius from the origin, this is R less than A here in this case, there is no charge enclosed. And this tells me that the total field will be zero. So the total field inside this one is zero, and it makes sense. Because if you put a point charge here, a test charge, you can see these charges are repelling it in the same way in all directions. So it will see a zero net force. Okay, now, and I'll explain this in a second. Now, if we select a Gaussian surface with radius greater than A, then we apply Gauss law. The integral of d dot ds is equal to the charge enclosed. The charge enclosed is equal to rho s, the surface charge density, multiplied by the total area, 4 by A squared here in this case. And then we can get the expression for the field. So this is what we do. First, if the radius is less than A, so the Gaussian surface is inside the charge, there is no charge enclosed. And Gaussian law is saying the integral of d dot ds is equal to 0. But because d must be in the direction of ds, and d is a constant, so this dot product becomes a scalar product, and I can take dr out, and because the area of the Gaussian surface is not 0, dr must be 0. So this is telling you inside this charged shell there is no field. There is no field, because if dr is 0, then er is 0, and this makes quite sense. Because if you put a point at the center, it sees equal force from all these charges. Now, if we select r greater than a, and this is the other way I explained, the same applies. The dot product becomes a scalar product. Take dr out. ds is equal to 4 pi r squared. The charge enclosed is the total charge on this sphere, which is 4 pi a squared rho s. So I end up with this expression. Divide this side over this side. So after division, this is what you'll end up having. This is dr. This is dr. This is a component dr. So d as a vector is equal to this component in the r direction. If you want to get E, unless otherwise stated, it's free space. It's d over epsilon naught. And of course, you divide this term here by epsilon naught to obtain the value of E. So outside this thin shell, there is field. Inside, there is no field. Now let's see a second example. We have a region. This region is a cube. It has sides 8, so extending from -2 to 2 in the x, y, and z directions. And inside this cube, there is this electric field, rho squared over 4a rho plus sine by z over 4az. And we would like to find the total charge within the cylinder, whose radius is 2, and whose height is along z from -2 to 2. So this is a typical nice application for Gauss law, because if I want to get the total charge inside a closed surface, I simply can get the total flux coming out from that surface. This will give me the total field. So we'll start first by drawing a diagram to see the expression that we notice, and notice here that we get to notice that we have here only a rho and a z components. If you draw a diagram, you will see this is your cube, and you will see that the cylinder is fully inside the cube. Then this expression for the electric field applies, and I can use it. I can try to calculate the total flux. Here we will have three surfaces, because we are talking about closed surface integral. We have the integral over the top surface. We'll integrate only here the z component of d. Here we integrate the negative on this one, the negative z component of d. On the side we integrate the rho component of d. Of course, each one of them has its own unit area. The unit area here, as we have seen before, this is d rho. This one here is rho d phi. So it is rho d phi. While for the side surface, it is this one here, and this one here is rho d phi, and this one here is dz. So it is rho d phi dz. And on the side surface, of course, rho is a constant. On the top and the bottom surfaces, z is a constant. So we start first by calculating d. D is equal to epsilon naught E. So the expression that we have for E is multiplied by epsilon naught, because Gauss law is applied to D, does not apply to E. So we now will say that the total flux out is equal to the flux over the side wall, the flux over the top wall, the flux over the bottom wall. And as we have seen, this one has a unit area in the positive z, this one has a unit area in the negative z, this one has a unit area in the rho direction. So now we substitute. The integral over the side wall will give us z will go from -2 to 2, phi from 0 to 2 pi. Your field value, remember, is rho squared over 4. E rho is rho squared over 4. And on the side surface, rho is equal to 2. So we are actually integrating 1. This is why you get this one here. And because the unit area is rho d phi dz, and rho is equal to 2, you can see I substitute here for rho to be equal to 2. So this is your integral on the side wall. On the top plate, your unit area is rho d phi, and here z is equal to 2. If you put here z equal to 2 for the ez component, you get sine pi over 2. Sine pi over 2 is 1. So the z component on the top plate will give you 1. Now in the bottom plate, z is equal to -2. So this term will give you sine minus pi over 2, so it's going to give you -1. But the unit area is also pointing in the negative z direction, so you get negative. So you get double this answer. This one and this one are the same, the top plate and the bottom plate. This one here will give you 2 multiplied by 2 pi multiplied by 4. We should be able to calculate these integrals now in a fast way. You get 16 by epsilon naught. Each one of these will give you 2 multiplied by 4 by 2 pi multiplied by epsilon naught, so 4 by epsilon naught. Then the total answer of the charge enclosed is 24 by epsilon naught. So here what we did, we calculated the total flux out of the cylinder by in order to get the total charge, and the same result is the same. The total flux will give you the total charge enclosed according to Gauss law, which is here equal to 24 by epsilon naught in this example.